Hello, this is again a class on statistical physics for my MSc students of SEM 2, and we would be dealing with chemical equilibrium because we have studied already the grand canonical ensemble and we have learned the meaning of the chemical potential. Then we can have a kind of rather deeper inner meaning in the case of chemical reaction. Let us see how. So we are studying chemical equilibrium. For better understanding, I would refer to section 6.6 of the textbook Archipatria. Okay, so let us try to first of all understand the meaning of chemical potential. Chemical potential actually determines the amount of the particular chemical present in a chemical reaction in equilibrium. Chemical present in chemical equilibrium. Now let us consider a chemical reaction we have let's say a chemical reaction with nu A molecules of A combined with nu B molecules of B, and that is going to give us a reaction, chemical reaction, reversible reaction with nu X, nu Y. Let's say this is a chemical reaction, and nu are the stoichiometric coefficients. We can call nu to be the stoichiometric coefficients, the amount of the particular molecule required for a chemical reaction. And let us assume that the corresponding number of the molecules initially present, initial number of molecules Na0, Nb0, Nx0, Ny0. So after performing delta n number of reactions, after delta n number of reactions, chemical reactions, so the number present would be, now the number Na would be equal to Na0 minus nu A delta n, Nb would be equal to Nb0 nu B minus delta n, and Nx would be equal to Nx0 plus nu x delta n, and Ny would be equal to Ny0 nu y delta n. And if the delta n is greater than 0, then the forward reaction, in which this is the forward reaction F, and if delta n is less than 0, then backward reaction. This is the backward reaction. Now we can say that the reaction would reach an equilibrium, in chemical equilibrium, when the delta G would be in such a fashion such that the delta G is less than or equal to 0. So we can say, and at equilibrium, this was at the time it reaches, and at equilibrium delta G must be equal to 0. So what is delta G? We know from thermodynamics, G is equal to A plus PV, which is equal to E plus Ts, E plus Ts, E minus Ts, E plus Ts or minus Ts, E minus Ts, right? PV. So dG would be equal to, I can call this as the internal energy U minus Ts. Okay, du minus TdS minus SdT plus PdV plus VdP, and du according to the first law of thermodynamics is given by du is du minus TdS is equal to minus SdT, so that is plus PdV. So this plus this is going to give us mu dN minus SdT plus VdP, because first law of thermodynamics, according to that, dq is equal to du plus PdV plus mu dN. Okay, and this is equal to TdS. So du minus TdS plus PdV is equal to mu dN minus mu dN. Okay, so this would be mu dN. So this is going to give us dG to be equal to 0. So the reaction, the chemical reaction is actually occurring at constant temperature and pressure condition. Chemical reaction normally occurs at room temperature and at 1 atmosphere. So T is equal to constant, P is equal to constant. So what we can say is isothermal isobaric condition for that dG, which is equal to 0, gives mu dN to be equal to 0. So we have achieved a condition for chemical reaction to be mu dN to be equal to 0 for all the chemical species, and here then we can apply this to our present chemical reaction, where we can write this to be equal to mu A. So applying this to over here, mu A of N A 0 minus Na plus mu B of NB 0 minus NB plus mu X of Nx 0 minus Nx plus mu Y of Ny 0 minus Ny must be equal to 0, and that gives us mu A plus mu B minus mu X minus mu Y to be equal to 0, and so we reach at a condition that mu alpha to be equal to 0 for a given species. This is the condition for chemical equilibrium. Well, do you know some 100 years ago what happened in the history of University of Calcutta Physics Department? It was in this particular year, in the year 1920, when Saha, one of the faculties of the Physics Department, Calcutta University, went out abroad to really enunciate his famous Saha ionization formula. Not enunciate, he already did his work and he went on to elaborate on those. The basic scheme was to compare the ionization in distant stars of different elements and compare them with the chemical reaction which we just studied a moment ago, and find the ratio of the ions to the ratio of different species of ions. It could be the ratio of Ca plus by Ca, or Ca double plus by Ca plus, or protons with respect to hydrogen, and so on. And by using those ratio, by calculating this ratio from the distant stellar spectra obtained, one can calculate the temperature and the amount of the element present. One can even calculate the age of the stars, which is again given in the section 9.8 of the textbook of Pathria. You can go through that. Right now we would be deriving the Saha's ionization formula by using the grand canonical ensemble which we learnt, and the formula for chemical equilibrium. Let us begin with that. Saha's ionization formula. What we can assume is, in the beginning, that the elements and the corresponding ionized form ions present in those distant stars are basically particles of the ideal gas. This is simply because of the high temperature and very small density, neutral atoms, assuming that they are at very high temperatures, and the corresponding density is also very high. So we can assume a classical system of particles in a classical ideal gas, and we can say that the partition function, canonical partition function, is given by V by h cube twice by mkt to the power 3 by 2, which can be written as V by lambda cube, where lambda is the thermal de Broglie wavelength. We know that, and that can be called, that particular volume occupied by a de Broglie wavelength, lambda cube, we call that as sigma. Okay. Now we want to calculate the corresponding grand partition function, which is the grand partition function according to the grand canonical ensemble, can be written as grand partition function can be written as double Q, which is basically equal to summation of z to the power n, okay, and q1 to the power n by n factorial summation over n, okay, where z is the fugacity. Z is the fugacity of the system. So we can write this z was equal to e to the power mu, e to the power beta mu, okay. So it was e to the power beta mu because it was e to the power alpha, e to the power minus alpha, which was equal to e to the power plus of beta mu. So we can write this as summation over n e to the power beta mu, and this is equal to q1, so this is equal to v1 to the power n by n fact v1 or v by sigma, okay, v by sigma to the power n. And so we can write this to be v by sigma. So one can write this again to be beta mu whole to the power n, okay. So this can be written as exponential of e to the power beta mu v by sigma. This is the grand canonical partition function. We can then define the q potential, which is equal to ln of the grand partition function, which would be given by e to the power beta mu v by sigma, and this can be equated immediately to the pressure PV by kT. So this is going to give us again P. So from here we can write the pressure exerted, VV cancels out, and this is equal to kT e to the power beta mu by sigma. So this is equal to e to the power beta mu by sigma beta, because 1 by kt inverse is beta. So now we can write this to be equal to n kT, because we know that ideal gas equation is n kT, where n is the number density, okay, number per unit volume. So we call this n to be the number density, and I am not writing n is number density. Okay, so we can write, comparing again, n, so this can be again written as n by beta, because 1 by beta. So comparing this, we get n to be equal to e to the power beta mu by sigma, and since e 1 by sigma is volume, this is number density, and this is an exponential quantity, so we multiply it with a number, which could be the number, quantum mechanical number, or any number arising due to the internal degrees of freedom. As we have said earlier, that if there exists an internal motion between the particles of the system, then that can be taken into account by putting it appropriate parameter within Q1. So now we are putting in the appropriate parameter n, which is the number, and dimensionally also this is number per unit volume, this is volume, this is an exponential quantity which is dimensionless, so this should be again a number which varies according to the Boltzmann distribution law. So we can write this, and so now we can say that mu is equal to 1 by beta ln n sigma. 1 by beta is n sigma by n. Okay. So this is our chemical potential for the gases which are present, or the chemicals which are present in the distant stars. These are the distant star chemical potential. So now we can apply the corresponding, if they are in chemical equilibrium, then we have mu alpha to be equal to 0 for all the species. So we can say that alpha, nu alpha, and ln of n alpha sigma alpha by n alpha, and there is a 1 by beta factor, but this doesn't depend on the type of the species. This is only dependent on the temperature and the Boltzmann constant, so we can take it outside the summation. So we can say this to be equal to log natural of 1, and we can write this to be equal to ln of pi over alpha, n alpha sigma alpha by n alpha whole to the power nu alpha to be equal to ln of 1, where pi is nothing but the product of the parameters as we had used earlier. So from this equation we can write pi of alpha n alpha to the power nu alpha to be equal to if you take logarithm from both sides, taking out logarithm from both sides, this is 1, so that would be equal to n alpha by sigma alpha to the power nu alpha pi over alpha, and this n alpha is the number which varies as n alpha 0 e to the power minus beta epsilon alpha. So now if we have a chemical reaction like this, x plus y is equal to xy, then we can always write from the above equation, from here we can write for this chemical reaction in equilibrium to be equal to nx ny, okay, and divided by nxy, because product would be negative, so division, logarithmic division is nothing but 1 by nxy, so that would be equal to n of alpha x, n of alpha y divided by n of alpha xy, and similarly sigma xy by sigma x into sigma y e to the power minus of beta and then epsilon x plus epsilon y minus epsilon xy. So that should be the relation. So for a distant star, the ionization for ionization in a distant star, we can always write x plus e minus is equal to x, okay, x plus electron is equal to x, and we can roughly say that the de Broglie wavelength, the volume associated with the de Broglie wavelength of the ionic species is equal to the volume associated with the neutral species. So with this, if we want to write the nx plus ne minus divided by n of x would be equal to, if I call this whole factor as gamma, this thing as gamma for this particular species, and sigma of x divided by sigma of x plus sigma of e minus, so these two according to this would cancel out, and e to the power minus of beta of epsilon I, where epsilon I is the energy for ionization, energy. I call it simply the ionization energy, okay. Now we can always express in terms of the fraction. If I define f to be, okay, there is another thing to be remembered, which is as follows, that for electrical neutrality of the stars, we can always say electrical neutrality of stars, we can write in x plus concentration of the ionic species is equal to n e minus concentration of the electron, because each ion is going to give us one electron. And now if I define the fraction f as the nx plus by n total, if n total be the total number of the species element, type of element, and that should be equal to n e minus n total, because we have nx plus, and then we can say that the total number of elements, then what would be nx? Now nx would be equal to 1 minus f, so we can write this to be equal to, from here, and using this we can write f into n total into f into again n total divided by 1 minus f of n total, and that should be equal to gamma of by sigma of e minus and e to the power minus of beta ei. And now we can say that f square by 1 minus f is 1 in total cancels out, and so this would be gamma sigma e minus n total e to the power minus beta epsilon I. So this is nothing but the Saha's ionization energy, which actually gives us the fraction of the ionic species which are present in those distant stars. I would like to add in conclusion that in the starting from the year 1920, just 100 years from now, it was first the discovery of Saha's ionization formula. It's a world-renowned formula for stellar spectra, for predicting the stellar spectra. Then came in 1924 the Bose-Einstein statistics, although by then S.N. Bose went to Dhaka University, and after that came the Raman effect in the year 1928. So the decade which started from 1920s to 1930 was a very important historical decade in terms of the discovery, new discoveries in physics in the University of Calcutta. I hope that could inspire you people to do something new for your university. Thank you.